here, what's different is the initial kinetic energy is not zero. I'm throwing it up at 20 meters per second initially. So my initial kinetic energy, instead of zero, would be 1/2 m times 400. Because it's 1/2 m times 20 squared. So my initial kinetic energy is not zero. And what else is different about the problem? Well, over here, my change in position is not negative anymore. My change in position is actually positive because I'm going up 1.5 meters. So the distance that I traveled up was 1.5 meters and not 2. And it was positive, not negative. The force of gravity is still negative. So that's a negative sign because the force of gravity is down, but the change in position was positive. So this term, minus 1/2 m times 400, trickles down. So I get minus 1/2 m times 400. The mass still cancels for everything. And I will move the 1/2 times 400 to the other side. So 1/2 times 400 is 200. I'll move that to the other side. So we get 200 minus g times 1.5 equals 1/2 v squared. And now finally to solve for v, I could actually calculate a number for this. G times 1.5 is 15. 200 minus 15 is 185. 185 times 2, to get rid of 1/2, equals v squared. And then take the square root to get v. You should get about 19.3 meters per second. Okay. One thing that you're going to notice when working with problems with gravity is that the way that you calculate this work of F dx, that side of the equation is going to be kind of repetitive. It's going to be the same way every time. So people have invented something called potential energy, which is a shortcut basically for calculating the work. Notice that this work done by gravity is always going to be, at least the work done by the force of gravity near the surface of the Earth, is always going to be mg times the integral of dx, or mg times the change in position. So this work done by the force of gravity, you could almost just, if you like, remember that term as the work done by gravity is always going to be mg times the change in position. So the work done by gravity, mg delta x, and you might have remembered that from physics 1 as the gravitational potential energy is mgh, or something like that. Does that ring a bell? Did you cover potential energy in physics 1? It's the same thing. You don't need the concept of potential energy. It doesn't add anything new to the problem. It's just repackaging the work done by gravity. Now, potential energy does have one other wrinkle. It says that if the concept of potential energy is that if I put energy into something, I can get that energy back out. So if I take work to raise my marker up, so suppose I take 10 joules of effort to raise the marker up. That means when I let go of the marker and the marker falls, I'll get 10 joules of energy back into speeding the marker up as it falls back down. So the work that you put in equals the work that you get back out again. I'll talk a little bit more about potential energy maybe on Wednesday. But the first thing you need to know about potential energy is that there's nothing to it, really. It's just a repackaging of work. The key relationship is that the work done on an object equals its change in kinetic energy. Whether or not you choose to repackage the work done in terms of kinetic energy is kind of a rephrasing thing. That's personal preference. You don't need to do that. Let me look at another example. And I'll do one more example with work before I come over to an impulse problem. So I'm going to erase all this. And I'm going to take an object, mass 2 kilograms, I'm going to drop it 3 meters onto a spring. So it's a little platform with a spring here. The spring has a spring constant K equal to 200 newtons per meter. I'd like to figure out how far the spring is going to get scrunched before it turns around and starts to push the mass back up again. So what's going to happen, the ball's going to come down, hit the spring, it's going to squeeze, and boing, send the mass back up again. I'd like to know the furthest the spring has scrunched. So the spring is going to be scrunched down to like there or something like that. And I want to know how far did that spring get scrunched. Okay? Everything about this problem is in terms of distances. I know how far it fell. I'm trying to find out how far the spring was scrunched. And the force of a spring depends on how much it's been scrunched. What is the equation for the force that the spring pushes back on something in terms of how much it's been scrunched? No. Looking for force. Almost. So suppose I have a spring, and suppose I'm standing at the equilibrium position, and I move in the positive direction. So the spring is attached to me over there. Which way will the force be applied to me? Which way is the spring pulling on me? So that way, negative. So if I walk in the positive direction, the spring is going to pull me in the negative direction. On the other hand, if I walk in the negative direction, it means I'm squishing the spring. The spring is going to push me back that way. So if x is negative, the force is positive. If x is positive, the force is negative. So the force acting on a spring is minus kx, not kx. It is not kx squared. If it were kx squared, then it would always have the same sign, whether I was positive or negative. A negative number squared is the same as a positive number squared. It turns out Ryan is thinking of the potential energy stored in the spring as 1/2 kx squared. But we don't need to know that to do this particular problem. I do need to know the force relationship with the spring. Okay, so what we'd like to do is use the same procedure. Work done on the mass equals the change in kinetic energy of the mass. What is the kinetic energy of the mass when I first let go? 0. What's the kinetic energy of the mass at the end, right here, when it's scrunched as far as it's going to go? I think you're right, because I think I said change in kinetic energy. What's the kinetic energy when I let go is 0. What's the kinetic energy, not the change in kinetic energy, what's the kinetic energy when the spring turns around and starts to push me back the other way? 1/2 mv squared. No. Well, I mean, sure, it's always 1/2 mv squared. How about, let me ask you this question. At the top, how fast is the marker going?
0.
So what's the kinetic energy of the marker at the top? 0. So suppose I go the other way. I'm going to bounce off a spring. When the spring is scrunched the most it's going to be, the marker is neither moving down nor up. So at the bottom, the speed of the marker would be 0. So the velocity of the marker at the bottom is 0. So therefore, what's the kinetic energy of the blob at the bottom?
0.
So my change in kinetic energy is 0 minus 0. Or 0. So between the top and there, the kinetic energy has not had any net change. Did the kinetic energy change between here and point E? Sure, it did. It sped up, sped up, sped up, sped up. Then as soon as it hits this, it slows down, slows down, slows down. So between here and there, the kinetic energy change is nothing. All right, how about the work done on the mass? Does the spring do any work between here and here? No, correct. So I can ignore the spring for this first section. Does the force of gravity do any work between here and here? Just yes or no?
Yes.
Yes. Does the force of gravity do any work between here and here?
I don't know.
Don't know. Fair answer. Okay. Is the force of gravity still acting on the mass as it goes from here to here?
No.
Does gravity get shut off? Somebody like Obi-Wan Kenobi in the Earth's center, like shuts off gravity as it goes from here to here. No. So the gravity is still in full effect between here and here. So the Earth's gravity is acting on the blob from here to here and from here to there. So the Earth's gravity is acting that entire distance. So when I look at the work done on the mass, I need to consider the work done on the mass due to gravity plus the work done on the mass due to the spring. In the case of gravity, the work acting on the mass is the integral of negative mg dx. So the negative mg comes out, and I integrate dx. The integral of dx will be x final minus x initial. X final minus x initial is just delta x, just like it was for the previous two problems we did. So yes, I went pretty fast through that, but we've been through it 2 times in the previous. Is the change in position positive or negative for the mass? In other words, does it go up or does it go down? It goes down. So that's going to be negative. Negative times negative is going to make it positive. Let's give this question mark a name. Let's call it x. What is the total change in position of the blob in this problem?
3 meters plus x.
Yes. It went down an amount of 3 plus x. It went down 3 plus an additional x. So the work done by gravity turns out to be positive. The reason it's positive is that the change in position was negative and the force of gravity was negative. When positive work is done on something, that causes it to speed up. The change in kinetic energy is positive. So the force of gravity, not the spring, just the force, just the work done by gravity is going to be a positive number, which makes sense. Gravity would tend to speed this ball up. So if there were no spring there, we just go faster and faster. Okay, next, I need to take into account the work done by the spring. Okay, so I need the force of the spring acting on the mass times dx. The force of the spring acting on the mass. What should I put in for the force of the spring acting on the mass? What relationship? Yep. Times dx. Now, the actual sign of that negative kx should be dependent a little bit on how the problem is oriented. The change in position from here to here perhaps will still consider to be going from positive to a negative number. Is the spring going to be pushing up or pushing down on the mass? It's going to be pushing up. When the dust clears, are we expecting this term, the spring term? When we're all done with this problem, should the work done by the spring be positive or negative?
Negative.
It would be positive if it's speeding the object up. It should be negative if it's slowing the object down. So all said and done, when the dust clears, however we work this out, should that spring be acting to slow the object down or speed it up as it's falling from this position to that position?
Slow it down.
So slowing it down. Okay, so when we look at these signs, we should pay close attention at the end and see if we need to fix anything. Maybe some of you can see, right now I've decided I've labeled the force as a negative kx, but I haven't been clear what exactly I mean by x. this x is the total distance the spring has been stretched. So this x is not, it's just one number. This is a variable that's changing as the spring gets stretched more or less. Okay? Let's evaluate this integral. K is a constant, so the k comes outside, and the integral of x dx. And my limits, well, I'm going from this to there. That coordinate would be, well, there's two ways you can do this. One is, but unfortunately they don't give the same answer. If you use the whole thing of 3 and then 3 plus x as your initial being a negative 3 and your final being a 3 plus x. From the perspective of this equation, that's treating it as if the spring went all the way to the top. And you went from stretching it from 3 to 3 plus x.
Should it still be
That's
negative?
not what we actually did here.
Should it still be negative k?
Yeah.
Okay.
We're going to think about that again though at the end.
Yep.